Welcome back from that break. Let's get into the next part of how we're linking the electrolytic cell to the table of standard reduction potential table. So this is the link we're making. We're making the link between the table of standard reduction potentials and electrolytic cells. And we've already done this writing down of the net reaction for the electrolytic cell. And what I want you to have noticed is that it wasn't following the same pattern as for the galvanic cell. That's important. We're going to see another difference shortly. So the next thing is to determine which ions will actually react. And so I've chosen another example. I've chosen the example of the electrolysis of sodium chloride. Now, this particular example is just taking some table salt, putting it into a beaker and putting some electrodes in, graphite electrodes, connecting the wires to a battery, and what do you think you'll get? Well, if we have table salt, we'll get sodium ions in the liquid, dissolved in the solution, and chloride ions. We put electricity through, what do you think we should be getting? Well, let's see what it looks like. And lo and behold, on these graphite electrodes, we get a gas here and we get a gas there. That wasn't expected. I'm sure you were thinking that you should get sodium at one side and the chlorine gas at the other. Well, for some reason, it's not working like that. So we have to explore and investigate a little bit more. How would we do this? Well, even here, the gases might be mixed up and we wouldn't be able to smell the chlorine and whatever other gas, I don't know what it could be, but let's find out by looking at the standard reduction potential tables. So remember what we started with? We started with sodium ions and and chloride ions in the solution. Run my finger down and there's sodium. It's not sodium ions, it's not what we've got, but I'm going to highlight it. And we're going to carry on and we're going to get to this point. And I noticed that we've got water there. We've just seen that one. And what's in the solution? Well, of course, there's water there. So it's possible that the water is reacting and the sodium isn't reacting. Let's think about that. And if we carry on all the way down to the next slide, there's nothing over here. There's some hydrogen, but there's no water. There's no water there. Go on to the next part. We run all the way down till we get to the chloride ion. And we therefore see that that's producing chlorine gas. We're going to need to write that and change it around, but let's select the equations. So this is my strongest reducing agent. On the other slide, I'm going to need to find an electrode that is going to give me, starting with the strongest oxidizing agent. Now remember, on this side, the oxidizing agents are getting weaker and weaker. This is a weak oxidizing agent. This one is slightly stronger, so it's going to be preferred. So this reaction is chosen above that reaction, and we'll discuss that shortly as well. But it will give me hydrogen gas and some hydroxide ions. So I can take those two reactions and write them one below each other. In this case, the chloride ion is what we're going to start with, and we're going to produce chlorine gas. The water is what we're going to start with over here, and we're going to produce hydrogen gas. So we know that this is going to take place. This is a reduction reaction. This is going to be at the cathode, and this reaction is going to be at the anode. So we've determined that the sodium ion is not involved. And there, as I said, because it's a much weaker oxidizing agent than this. So in that way, we can determine which ions are reacting. To help us, we're going to do one last thing with the table. And that is, if we look at these reactions, we could add them together and we can get the net reaction. I've rewritten them like this, so we can find that what we've actually got is that the electrons are the same, and we'd have to make sure that we're starting with the chloride ion, switch that around, and we'd be able to add them together. The electrons would be the same, we'd write it that way. Chlorine is actually the thing that's being produced. Hydrogen is the thing that's being produced, and we've got the hydroxide left over. When we look at the last linkage, it will really help us focus how things will fit together. because this is the calculation of the E naught of the cell, or the EMF required to make the cell operate. And what we'll see is that without us putting energy in, we're not going to get a reaction. And so that's why the pattern has been the opposite way down, with the reducing agent down at the bottom on the right-hand side and the oxidizing agent up at the top. Let's calculate the E naught of the cell. So that's what we're going to look at. This is actually the E naught, the EMF of the cell. In this case, the electrolytic cell needs some energy coming in. The calculation of the E naught tells us what's the minimum potential difference that's required across these electrodes. If we don't use enough energy, the reaction wouldn't take place. So that's why this equation is so important. Let's understand it. Notice it's exactly the same as what we used for the galvanic cell. The E naught of the cell is equal to the E naught of the cathode minus the E naught of the anode. So when we look at that, we are going to use the example of the electrolysis of copper to chloride as our example. Remember that the anode was where we got the chlorine gas being produced, and the cathode was where we got the copper being formed. So we just want to make sure that we annotate that correctly, and we're going to say the copper was formed at the cathode. So in our table, we're going to be looking for the things that we started with. What we started with was with copper ions and chloride ions. So we run our finger down the table, and we have done this before, and you'll be quite clear that we can't see any copper ions on the right-hand side. Go to the next slide of the table, and we will see that copper metal sits over there. That's not what we want. We know copper metal is the thing that's being produced. They're the copper ions. They're on the wrong side of the table. So copper isn't the reducing agent here, or copper ions. We're not going to worry about them. They aren't going to be involved in the oxidation reaction. Carry on going down, and there's the chloride ions. The chloride ions are the strongest reducing agent. So they are going to lose electrons. They're going to donate electrons in this process. And when they donate electrons, that's going to form the product, and the product I'm going to circle in blue is chlorine gas. And the product that is formed on that reaction is going to be copper. So we recognize that what's circled in red are the reactants, and what's circled in blue is the product. It's very important to notice in this particular case, the position and the order of the reactants and the product is opposite to what it was for the galvanic cell. In fact, if we draw a line between the two reactants, we'll see that it forms a line with a negative gradient. It's needing energy. Energy has to be put in. It's not going to be spontaneous. And so remember this case, if this is the reaction, we recognize that's the reaction that is oxidation, and that takes place at the anode. This reaction is going to be the reaction of reduction, so it's going to be the cathode. So it joins my attention now to the equation where these numbers come into play. That's the cathode, and this one over here, plus 1.36, is at the anode. So I've written it down for us to have a look at. We've got the chlorine being produced over here. The chloride ion is the thing that's reacting. That's going to be the anode. The anode value is plus 1.36, where the cathode value is this one. So we're going to substitute those values into the equation, which we've done over here. So we're taking the value from the cathode, substituting it into there, subtracting the value of the anode. Now, I like to put that in a bracket because sometimes we are going to have a negative in there. So we're going to go to minus, minus, and remember that's going to be a positive. In this case, it's not. So let's call up the calculator and let's do that equation very quickly. And so we're starting with 0.34. We're going to subtract 1.36. And look what we get. We get an answer of minus 1.02. So minus 1.02 volts. Do you remember that for the galvanic cell, we always got a positive value? Here we're getting a negative value because it's not spontaneous. We're going to put in energy, and the minimum amount of energy is a value of 1.02 volts. Without that, the reaction won't happen. That's why this is called an electrolytic cell. It's not spontaneous, and the E naught of the cell is a negative value. And that line linking the reactants has a negative gradient. So it all works together, helps you remember the difference between electrolytic and galvanic cells. And so that brings us to the summary for this section on introducing the electrolytic cell. Remember, an electrolytic cell transforms electrical energy that we're going to put into the system into chemical potential energy. What that means is electricity produces products, new chemicals. So we could start with a compound and we'll get elements, or we can start with compounds and get different compounds that are forming. Notice that the E naught of this type of cell is negative. That tells us it's a non-spontaneous reaction. But remember what's similar between the galvanic cell and the electrolytic cell is that oxidation always takes place at the anode. We remember that we're looking for an ox. We recognize reduction is at the cathode. We're looking for the red cat. Guys, that wraps up all that we need to be saying about this reaction. I hope that you've enjoyed looking at electrolytic cells, and we'll see you again shortly.